All right, so let's look at the second lecture in 16.3, and we're looking some more at vector fields, and really we're looking at when do we find a vector field as a gradient of a certain function, say phi, doesn't really matter what you call it, just the potential of this vector field. Now, we saw some conditions on derivatives that were saying that maybe we could integrate, we could find this antiderivative, but I said it doesn't always work. So it's the right way of the right place where it works are so-called simply connected regions. So a region is simply connected if every closed path can be deformed to a point. And this deformation has to be, we're not allowed to break the path. It's supposed to be a closed path, some sort of loop, right? And we're not allowed to cut it, or do something, or split it into a couple of pieces. We're only allowed to sort of continuously move it about, and its origin is simply connected. If you have this any sort of loop that you can continuously scrunch it down to a point without leaving the region. Maybe let me emphasize it, without leaving region. So for example, if my region is it's going to be maybe a little hard to imagine, but imagine this pen is infinitely long. It goes on forever. All right, and so maybe I actually have a easier with a pencil. So I have a pencil here. Right. So imagine this pencil goes on forever, and that's. So imagine our region is the outside of this pencil. The pencil is not in our region, right? Then suppose we have a loop, like this rubber band that goes around the pencil, and the pencil is infinite. It goes on forever on both sides. It is impossible to get this rubber band and scrunch it down to a point. It's always going to go around this pencil, right? I would have to sort of go infinitely far. If this pencil really is infinitely long, right, I cannot just take it off like this, right? Because there is no end to the pencil if it's infinitely long. So the only way I could do it is basically break the rubber band and take it off, right? And then I could scrunch it down to a point, right? If I wasn't missing this pencil, this line, then I could, right? I take any old, it can be sort of, in some complicated way in the plane, and I could slowly move it and scrunch it down until it's a single point, right? Hard to do with an actual rubber band, but I don't have to break it, right? So the entire 3 space is simply connected. 3 space minus an infinite line is not. It's even easier in a plane. In a plane, a region is simply connected if it has no holes. It's maybe not exactly a technical term, no holes, but basically, you know, it's if I have a region and it has a hole, so maybe the region is this thing, this hole is not in my region. This is not simply connected because I could put a loop around it, and there's no way that I can move this loop to some point, let's say over here, and just crunch it down to this point. It's always going to want to go around this this hole, right? I would have to break it somehow. So that's what simply connected is, right? And so what is the result? So the result is that, and this is a theorem, right? So in a simply connected region, F is conservative, meaning it has a potential if and actually, you know, this goes both ways. I'll write as if and only if we have these conditions that we talked about a couple of lectures ago, right? Which were basically, the thing was is that this was if we had an actual potential function, right, the actual phi, then these were precisely the conditions that the second derivatives, the mixed second partial derivatives, commuted, right? You know, the x and the y derivative, you know, it doesn't matter which way I take it in, right? That's what this is saying, right? Because f1 would be the x derivative of the potential, and f2 would be the y derivative of the potential, right? So if I take the y derivative of the x derivative, is the same thing as taking the x derivative of the y derivative, right? So this works in a simply connected region. So this is if we want to know if something is conservative, this is actually fairly easy to check. It's just a bunch of derivatives, right? Especially if I have some nice formula for f, this is fairly easy to check. All right. Make it easier for me to check my notes. All right. So. And it's easier than what we were doing last time, which was basically, well, we tried to integrate, right? Well, you can basically try to integrate, and if you fail, in that you come up with a contradiction that it's impossible to find an antiderivative, then you know that then you know that the thing is not conservative, or maybe you find find the actual potential, but integration is hard, right? This is much simpler, but only works in a simply connected region, right? Let's maybe do a couple of examples. Now, I should mention that if we're in the plane, it's just this first equation, right? Because in the plane there is no f3, so neither of these makes any sense, and there's also no z, so neither of these makes any sense, right? So in the plane, it's exactly just this first equation. So in the plane, it's even easier. You just take two derivatives, right? So let's do an example. Let's suppose we have f. Let's suppose this is y e to the xy plus 2x, and hopefully I've done this correctly before, and it is actually. All right, so let's try to find a potential here, right? So first, let's check if it's conservative, if it even makes sense. This is f1, this is f2. So d f1 dy, what is it? Well, it's I have to do product rule here. So it's e to the xy plus x e to the xy, right? And then plus the y derivative here is 0, right? df2 dx. So I wonder if I well, maybe this still might be a good example. So suppose that we have this, and I take the derivative over here, right? And again, I have to use product rule. So I have e to the xy when the derivative just hits the x, and then plus. I did miss the y. Okay, good. I was thinking I was doing something wrong. Yeah. It was a y here, right? Because I forgot about this when I do the product rule, right? So now it's gonna again make sense. So now I have the x, right? And I take the derivative of this thing. It's gonna give me a y, right? Okay, good. These are equal. Yeah. All right. So that means that we should be able to find find a potential. Well, why should we find potential? Well, what's the region? Well, this is defined everywhere. So our region is the entire plane, and the applied plane has no holes, right? By definition, we didn't take anything out, so we didn't take out any holes. So therefore, we should be able to do this antiderivative, right? So let's start. Let's suppose that we take. We know that this is supposed to be the x derivative, right? So if we anti-differentiate in terms of x, we should we should get at least part of the answer, maybe, right? So phi, whatever it should be, is the x antiderivative of this, right? So over here you see that this is precisely the antiderivative of e to the xy, right? Because if I take the derivative of with respect to x by chain rule, I will get that y coming out, right? Y is just a constant in this case, right? And over here I will have x squared, right? Well, I still have some possible constant with respect to and this will be a function of y, maybe. I don't know if I'll need it, maybe, right? So let's check. So what if I have d phi d y, which on one hand is supposed to be x e to the xy, because that's what it's supposed to be, and on the other hand, well, I can just differentiate this. I'm gonna get x e to the xy plus c prime y. Okay, so I could just make c constant, right? Because then c prime would be 0, and I would get that this is equal. So phi is really e to the xy plus x squared plus c, really some constant, right? It's not going to depend on x or y. Now, we could go, we could start on the other side. We could start with this guy, right? This is the derivative with respect to y, right? So I could say, well, phi, I could anti-differentiate this with respect to y. So phi would be, well, this is e to the xy, right? And that's the antiderivative, but I need to add the constant. Let me call it something else. Let me call it d. It's not necessarily constant so far. It's some function of x, right? I've anti-differentiated in y, so the constant is going to depend on x, right? And now I differentiate with respect to x, which on one hand should be y e to the xy plus 2x, and on the other hand, well, I'm going to get y e to the xy plus d prime x. Oh, well, now d prime x had better be 2x. So d of x, well, it's x squared plus some constant. I could even call it c because it's going to work out to be the same one as over here. And I'll have that phi as e to the xy plus x squared plus c, right? So I found the antiderivative, the potential. And it doesn't really matter which way I went, but you can see that the computation is slightly different. It's not always going to be easier if you do x first or y first, but you could see that I knew that it would succeed by taking, checking that condition in the theorem, right? On the other hand, and I'll let you do the calculation of this, but if I have if my f would be, and I'll let you do the calculation because well, maybe let me do it. Why not? We have lots of time. So suppose that we have just this f1, f2, right? Okay, this is the so-called vortex vector field. It's not defined at the origin, right? But it's defined everywhere else, and it's it goes around like this, except it goes slower and slower as you go further out from the origin, and it goes faster and faster as you are at the origin. This is precisely the rotation that you're if you are in the bathtub and you pull the plug, it's the water is gonna go in this vortex, right? It's precisely this thing, and it rotates much faster near the drain than far away from the drain. Okay, let's do this computation. If I take the y derivative of f1, so this is a quotient rule, right? So we have to take I have the derivative of the top, so minus 1 times the bottom minus the top times the derivative of the bottom, right? In terms of y, right? To y, right? and it's supposed to be x squared plus y squared square, right? Let's see, did I do that correctly? Derivative of the, yeah, right? And still, I think so. Well, we'll see once we do the second one if it works out. So over here we do the x derivative of this, again quotient rule, so it's 1 times x squared plus y squared minus the top x times the derivative of the bottom, now with respect to x, right? And times the bottom squared. Okay, maybe let's simplify these. So I have plus 2y squared out of this. I have minus y squared, so this is y squared minus x squared divided by x squared plus y squared squared, right? And over here I have the same thing, y squared minus x squared, right? Because it's minus 2x squared, and over here I have x squared. Alright, so these are actually equal, but this guy is not conservative. How do we actually tell that it's not conservative? How can we tell? Well, if it was conservative, then it had better around every loop, right? Remember last time? Around every loop, the integral had better be 0. So let's take the unit circle, right? And let's do the integral over the unit circle of f. Here's the book's notation, dr. Well, we have to parameterize the circle, right? So r of t, cosine of t, sine of t, and t, let's say from 0 to 2 pi, right? So we have the integral from 0 to 2 pi of f, right? So we have minus sine t divided by cosine squared t plus sine squared t, and then we have cosine t divided by cosine squared t plus sine squared t. Sorry, it's a little hard to read. The plus sign, dot, this thing, dot, the derivative of the r, right? So this is, maybe we make sure that we know that this all goes under the integral. So cosine minus sine t, cosine t dt, right? Now, if you look at this, I will have, this thing is just 1. This thing is just 1, right? Then I have minus sine, well, let me just write it. Let me get rid of this thing, it was just 1, right? So I have minus sine of t times minus sine of t. And plus cosine of t times cosine of t. Alright, well, but it's again just 1, right? Because minus sine t squared, the whole thing, is the same thing as sine squared. So cosine squared plus sine squared is 1. So this is the integral of 0 to 2 pi dt. This is 2 pi, right? Not 0. There is no way to find a potential for this, right? There is no phi exists, even though we are satisfying these things, and that's because it's not a simply connected domain. we could do it in a smaller region. We could find an antiderivative. Let's not try to do that. It would be sort of ugly, but we cannot do it in the entire punctured plane, right? In the entire plane minus a point. So let's give these kind of vector fields a name. So the vector field satisfying the differential conditions, and by those I mean these guys, right? If we're in 3 space, all 3 of these equations. If we're in the plane, just this guy. But a vector field that satisfies these guys is called irrotational, right? Well, I mean, conservative vector field is in particular irrotational. That's by this theorem, right? If we have or by just the computation that we did before. So if we have these conditions, then we have an irrotational vector field. But an irrotational vector field, so if we have a conservative vector field, then we have an irrotational vector field. But a irrotational vector field need not be conservative. This is an example of it, of one of these. Now, it's interesting that the water circling the drain is called an irrotational vector field. It seems to be rotating, but it's not. Rotating locally. This is the any sort of condition that is based on derivatives only sees something very locally, right? If we're checking it here, it only sees what's happening really in a small piece, right? It's not seeing the whole picture, right? Whenever you have any sort of differential equation, any sort of equation of derivatives, it's always very local. It cannot see the big picture. These kind of conditions, these kind of equations, are basically like being in a fog. You cannot see far. You can only see what's happening right next to you. And locally, this thing really is irrotational. If we put a rubber duck to circle a drain, what's interesting is that the rubber duck, it's pointing in a certain direction. As it will circle the train, it will point always in the same direction, right? Because while it's sort of rotating sort of globally, it's not rotating locally, right? Why can you see that? Well, if I'm, if the rubber duck is, I don't know how to draw a rubber duck. I don't know. That's the worst rubber duck, or it's from the top, So it's that's the hard part. The vector field, the rubber duck is going like this, but the inside vector field is faster than the outside vector field. So even though the duck is going like this, it's the duck is actually always pointing in the same direction, right? So, all right. So that's what it means to be irrotational. So irrotational just means that those derivative conditions, these guys are satisfied, right? It doesn't mean necessarily that the vector field is conservative, right? So this vector field is not conservative, right? The vortex vector field. even though it is irrotational. Now, if we have a conservative vector field, if we want to figure out what it is, there's another way of writing it out that sometimes might be more useful than trying to sort of do this guessing game. So suppose that we have an f, and let's suppose we're in the plane, right? So just f1, f2, right? And let's suppose that this is conservative, and we want to find a phi, right? Well, we know that the antiderivatives are always up to constant, so we could set phi to be something at some point. So, and let's suppose this is in the entire plane, right? In the entire xy plane. So what we could do is at the origin of 0, 0, we could just set it to be 0. Now, at xy, we're gonna, 0, 0, xy. What we're gonna do is we're gonna draw a straight line, and we're gonna let, we're using r. Let it be this path, right? Going from 0 to 1, right? Now let me even call this C, right? So that for the notation over here. So this path. So for each xy, I define a different path, of course, right? It's a straight line going from 0, 0 to xy, right? And it's given by this formula, right? Let's say if t is 0, I get 0, 0. If t is 1, I get xy, right? So that works. And then we write down so we have it at 0, 0, but at any other xy, we're going to integrate the vector field along this path. What does that mean? That means I'm integrating from 0 to 1 f of r of t, r prime of t dt, right? Now, let's maybe write down explicitly what this is, 0, 1. And then, what is r prime? This is kind of easy, right? It's because these are linear. Like r prime is constant, right? It's xy, right? So this is really f1 times x. I'll put the x up front, and then it's at tx ty plus y. That's 2. T. This y is coming from over here, right? Tx ty. All right. So now we have a formula. We can just this might be useful if you have either if you're doing something some theoretical result. You want a formula for any f. Or maybe in a computer, this is easier to write down. It's easier to have a computer to do this. You can write a little routine that gives you back potentials, right? And it can even approximate them numerically if you cannot do this antiderivative symbolically, right? It can tell you you can evaluate this numerically, right? Given any x and y, you can tell you what the potential should be, right? Or approximately, right? Going to approximate, even if you maybe couldn't do the calculus, right? Let's see that this really works. Let's do the x derivative. The y derivative is very similar. So let's suppose that we take the x derivative of phi. So how does this work? Well, it's the same thing as taking it's the x derivative of this whole thing, right? Well, that's just like taking the derivative underneath, right? So I have 0, 1. Now the x derivative, there's chain rule going on, right? So I'm gonna get f1 dy plus x, and now we have the x derivative of f1, and chain rule is gonna take out a t, right, like this, tx ty, right, plus, and then I do the x derivative over here. Well, y is a constant as far as x is concerned, so this is just y df2 dx. Now tx ty, and then chain rule, right? I still have to differentiate this with respect to x, and that is t again, so I'll put that up here, right? dt. Okay, now what happens is that now we use that this is well, this is irrotational. We're in the entire plane, so it's simply connected. So irrotational is the same thing as conservative if we're in the entire plane. There's no holes. So we have that y is the same thing as the f2 dx, right? Now, so for a conservative vector field in the plane, right, this is going to be true. So we can plug that in here. This is df1 dy, right? Let me maybe write that down, the whole thing. I really have a green thumb from the side. I always have a green thumb when using this pen. f1 tx ty plus tx df1 dx ty plus ty df1 dy, right? That's the same thing, because df1 dy is the df2 dx, right? Alright, well, now this looks like a different sort of derivative. One notices that this is like the t derivative of t f1 tx ty, right? Why would that be true? Well, first product rule, so that's why I'm getting this term, right? And then it's t times the derivative of this with respect to t, right? So I'm gonna get the x derivative times the derivative in the first variable. That's gonna give me an x coming out by chain rule, plus, so t times the y derivative of this, and then I also have to differentiate ty, is gonna give me y. Alright, well, this thing, that's just calculus 1. Right, I have a derivative of something integrated from 0 to 1, so I evaluated 0 to 1. Well, at 0 it's easy, it's just 0, right? It's 0 times, well, whatever, who cares? And 1, I get precisely f1 x, y. Yeah, that's what I wanted. That's what I wanted. Right? The phi dx. Hey, it works. So this is this might be a useful formula for the potential. If you know that you have a conservative vector, if you know that the potential exists. All right.